Example 1. A particle starts at t equals 0 and moves along the x-axis with a velocity of v of t equals t squared for time t is greater than or equal to 0. Where is the particle when t equals 3? This means that we're looking for the distance traveled over the span of 3 seconds. Your instinct might be to plug in 3 for t, but the problem is that will give you the velocity. So what we're looking for here is the distance traveled in 3 seconds. So I'm going to break this down into 3 steps. Step 1 is to draw a graph. So we're going to draw a graph, and we're going to let the horizontal axis represent t and the vertical axis represent v of t. So we're going to go ahead and we're going to draw out t squared. So when you have 1, it's 1. When you have 2, it's 4. And when you have 3, it's 9. So now we're going to sketch out that graph. And it looks something like that. So our starting point is 0 and our ending point is 3. So the next step is to partition the graph into a set of number strips. Let's say we're going to do 6. So what I want to do then is partition it up. Now remember, the area underneath this curve is going to represent the distance traveled in 3 seconds. So this highlighted blue region represents the distance that the particle travels in the first 3 seconds. You might want to make a note of that and actually write that down. The area under the velocity curve is the distance traveled. And this would even work if, for example, the graph sloped down, because it takes into effect negative distance as well, and we'll get into that later. So we're going to separate it into 6 vertical strips. This means that you're going to have 1, there's 3, so I need to cut each of those in half again. Now I've got equal distant rectangles. So in order to find this delta x, in order to find out what it actually is, we have a formula. The formula for delta x is b minus a over n, where b is the starting point, b is the ending point, and a is the starting point. This gives you the width of each partition, where a and b are the endpoints, and n is the number of partitions. So delta x is equal to 3 minus 0 divided by 6, which is 3 over 6, which is equal to 1/2. Step 3. Compute the area, or the RAM, the rectangular area method, for each rectangle. So remember, the area under the curve is the sum of the area of the rectangles. So here's my graph again. And I'm going to partition it up into half spaces. So delta x is 1/2. So I partition it up, and I get these gray points that align with the x values. So what I'm going to do now is draw rectangles. So I'm just going to use these as my endpoints of the rectangles. And there you go. Now you have rectangles. So if we look at these rectangles, this distance down here is delta x, and this distance right here is going to be f of x, depending on what the x value we used. So here, this is going to be x1, x2, x3, x4, x5, and x6. Notice that we have 6 x values for 6 partitions. So the area of each rectangle is then delta x times f of x. This is the base, and this piece right here is the height of each rectangle. So in order to find the area underneath the rectangles, you're going to add up all of the areas of each rectangle. So delta x times f of x of 1 plus delta x times f of x sub 2 plus delta x times f of x sub 3 plus ... all the way until you get to delta x times f of x sub 6. Now notice in each of these, you have a delta x. So to make our math a little easier, we go ahead and factor that out. Plus f of x sub 2, all the way until you get to f of x sub 6. And again, this is the base of each rectangle because they're the same, and this is the height of each rectangle. Now there are 3 ways to compute this. The first way is called LRAM. We're going to use the leftmost endpoints of each rectangle. So my first rectangle is going to start at 0. That's my first point. My second rectangle is going to start here. Third one's here, fourth one's here, fifth one's here, and sixth one is here. So the first rectangle has 0 area. It's just a straight line. The second rectangle has a little bit of area. The third rectangle, the fourth rectangle, fifth rectangle, and sixth rectangle. So underneath this is going to be the area that I'm going to add up. My goal is to add up to get all this blue area. Okay, so let's go ahead and compute all of that area. X sub 1, x sub 2, this is x sub 3, x sub 4, x sub 5, and x sub 6. Again, the left points. So then the area is going to be 1/2, because that's our delta x, times f sub x sub 1 plus f sub x sub 2 plus f sub x sub 3, and all the way until you get to 6. So it's going to be 1/2 times f of 0 plus f of 0.5 plus f of 1 plus f of 1.5 plus f of 2 plus f of 2.5. So remember that f of x is equal to x squared. Technically it's f of t, but the variable really doesn't matter too much. So you get 1/2 0 squared plus 0.5 squared plus 1 squared plus 1.5 squared plus 2 squared plus 2.5 squared. And you work that out and you're going to get 6.875. Now let me ask you, do you think that's an overestimate or an underestimate just by looking at the areas? It is an underestimate. So that's the first way. Now let's look at the second way. This is called MRAM, the middle points. So what you're going to do then is you're going to take points that are halfway between each interval. So I'm going to pick this one, this one, this one, this one, this one, and this one. And again, those are the halfway points. So this would have been 1/4. This one would have been 3/4, 5/4, 7/4, 9/4, and 11/4. So now we're going to draw a rectangle. And again, they go to each endpoint. So our goal now is to find the area underneath that rectangle. So take a second and try to do that on your own. Okay, now that's all worked out. Let's look at this area underneath the curve. Do you think it's a underestimate, overestimate, or a closer approximation of what the actual area is? So MRAM will actually get you closer than the LRAM. Now let's look at the third and final way. We've done the left endpoint, we've done the middle. Now we're going to do the right endpoint triangles. So now what we're going to do is we're going to take each point and we're going to use the right endpoints as our rectangles. So I go draw a rectangle straight across. This is the way we did the very first example. Okay, and we're going to do the same thing. We're going to calculate the area of all of these rectangles. So take a second and on your own calculate the area. And you're going to end up getting 11.375, which is, as you guessed it, an overestimate. And that's how you use partial sums in order to calculate the area underneath a curve.